Hi everyone. Welcome to Doris Summit Global 2022, and I hope you are all having a fantastic time at the conference so far. So in today's session, I'm serious to walk you through how we can bring real-time capabilities to data lake and ultimately shape the future of real-time lakehouse with Apache Doris. Okay, so first, let me introduce myself first. My name is Mingyu Chen. I'm the PMC chair of Apache Doris and also the co-founder and the VP of engineering at VeloDB. And VeloDB is a company built around commercializing Apache Doris. So as for myself, I've been working in the field of analytical database system for more than 10 years. And right now, my main focus is on technologies that enable real-time data analytics in the open Lakehouse ecosystems. Okay, so all right, so let's get into the main topic. So I'd like to start with a bit of background. So we'll first talk about where the concept of lakehouse came from and why the lakehouse is needed and which project in this space have been getting the most attention. So and at the same time, I also point out some of the issues and the limitations that still exist in these areas, which will help us better understand the challenge we are trying to solve. So the concept of lakehouse isn't really a new anymore. So at its core, it's really an extension of enterprise needs to analyze a massive amount of data. So at the beginning, we start with a high performance database. And then as the need for the low cost, scalable solution grow, so data lake emerges. The lakehouse is essentially about combining the best of both worlds, the data lakes and the database. So its core requirements are two requirements. So one is to have the low cost storage, elastic scalabilities and openness, and unified data storage of a data lake. And the second is to have the performance, transactional support, and the unified analytic capabilities of a database systems. So to sum up, so organizations need real-time analytics on massive dataset stored in data lakes without sacrificing the performance, the data freshness, or breaking the budget. So the lakehouse is really about bridging the gap between the data lake and the database. So the thing is, data lakes and database were originally designed for very different use cases, like I said before. So before the concept of the lakehouse came along, the enterprise faced a tough choice. So either sacrifice performance in order to get a flexible, low-cost data storage and processing by using data lake, or to give up flexibilities and pay higher cost for high performance analytics by using database. So over the past few years, so many projects have been trying to close this gap between the data lakes and the databases, so searching for solutions that can offer the best of both worlds. So among these projects, the iceberg is the classic example of the lakehouse solutions. So honestly, we should not call iceberg a lakehouse. So it is just a table format. And over the years, the iceberg has grown and ultimately outcomplete other lake formats, becoming the de facto standard for lake table formats. So why the open table format like iceberg is a big deal? So in fact, iceberg or other open table format, so along with projects like Delta Lake, Pymon, and Hoodie, is essentially addressing one key problem, the managing data files on the lake. So this is a fundamental element for data analytics. So back in the Hadoop and Hive area, so massive amounts of files were stored on HDFS or object storage. So, but there was no effective way to manage them. So no version control, no schema management, and no transactional guarantee. So while it was possible to store large volume of data at low cost, so the difficulty and the inefficiency of data management made high performance analytics nearly impossible. So the lake table formats like Iceberg introduce a table metadata management layers. So this allows transactional operations, schema, and version informations to be managed in a unified way. So by leveraging like partitioning and indexing information, they also provide efficient data pooling and management capabilities. So make the lakehouse vision achievable. Okay, so now let's take a look at the challenge that still remain when we try to build real-time queries on top of the lake format like Iceberg. So when we talk about the real-time queries, so we are usually referring to the high concurrency, low latency scenarios. For example, so hundreds or even thousands of concurrent requests with sub-second response time. And these are the kind of scenarios that a database is very good at. So, but providing the real-time analytics on a data lake brings several major challenges. The first is the metadata management. So the table format like Iceberg does give us efficient file management. But as data volume grows or write frequency increases, the things like manifest file booms, a loss of version files, and the accumulation of small files all start to slow down performance over time. And the second challenge is the I/O challenge. The lake tables are usually stored on shared storage storage systems, most commonly like AWS3, the object storage. So compared to the local disk used by many databases, the object storage have much lower performance in terms of like the IOPS, latency, and the random access. So this fundamentally limits the real-time query capabilities. And the last challenge is the query engine itself. So Iceberg only defines the table formats and the metadata management. The raw computation performance of a query engine directly determines how fast and scalable queries on lake table can be. So next, I will introduce Apache Doris and show you step by step how Doris tackle and solve each of these challenges. Okay, so let's move on to the why we should choose Apache Doris. So let me start by a quick introduction to Doris. So Doris is a high-performance analytical database, so which is own storage format and computation engine. So it offers a wide variety of data ingestion methods, so making it very easy to bring the data from mainstream sources and run high-performance real-time analytics on top of it. So Doris is also compatible with the MySQL protocol and supports standard ANSI SQL syntax. So that makes it very user-friendly for anyone who is already familiar with SQL development, and it's also simple to use. So, but today I want to highlight another major capabilities of Doris. So it can act as a unified query engine. So that means Doris can directly query external lake tables or its own internal table format, or even other data sources, and run arbitrary join queries across them. So in the next part, I will focus on how Doris delivers real-time query service on top of lake tables and how these capabilities help fulfill the vision of the Lakehouse. Okay, so first, let's take a look at what the Lakehouse architecture looks like when it built around Doris. So Doris is deeply integrated into the data lake ecosystems. So on the right side of this slide, you can see the Lakehouse architecture diagram with Doris as a core analytical engine. So broadly speaking, so this architecture is divided into several layers. So at the bottom, we have the shared storage layers, which is typically the object storage. And on top of that is the open format layers, which include the file format like Parquet and the table formats like Iceberg. And next to it, we have a catalog service, such as the traditional Helmet store or the AWS Glue, so which can handle the unified metadata management. And finally, on top, see the query engine layer. This is where Doris plays this role. So this architecture enables a number of important application scenarios. For example, the real-time dashboard on large-scale historical data, or the unified batch or streaming analytics, and the data lake acceleration without ETL, which means you don't need to copy the data from the data source to Doris before processing it. And the first one is the federated query across multiple data sources. So now, within this kind of architecture, let's go back to the real-time query challenge on lake table that I mentioned earlier and see how Doris address each of them. Okay, so the first challenge is I/O. So object storage can provide very high throughput, which is naturally advantage for the large sequential read. But however, for the analytical workload that involve a lot of random access, the IOPS and the latency of object storage often fall short of the requirements. So to address this, Doris implements two major type of I/O optimizations. So one is the optimizing the I/O access pattern. So to align with the high throughput nature of object storage, so Doris automatically detects the adjacent I/O request and merge the small request into a larger one. So this reduces the number of IOPS and increase the efficiency, effective throughput. So in addition, Doris launches a prefetching threads. So while the CPU is processing the current batch of data, the prefetch thread read the next batch of in advance, so making full use of available bandwidth. So this optimization significantly reduced the I/O request and dramatically increased the throughput. So the second one is using local caching for low latency. So simply increasing the throughput is not enough to solve the query latency issue. The high-speed local disk and the memory cache are critical. So Doris provides multiple levels of caching, like the metadata caching, the data file caching, and the query result caching. So to efficiently handle repeatedly access to hot data and deliver the low latency query responses. So furthermore, Doris has implemented deep optimizations for iceberg metadata access, including like the partition pruning, the manifest file caching. So these measures greatly improve the efficiency of accessing the lake tables. Okay, so the second aspect is data scanning and task scheduling. So in real-time analytic scenarios, we usually means online service, so which require the predictable query latency. So however, when accessing lake tables, a large portion of the latency comes from network I/O, so which can be unpredictable. So to address this, Doris introduced a priority-based task scheduling framework. So this framework is especially effective in mixed workload with both large and small queries. So for example, it prevents a single large query from occupying all threads and starving the small queries. So this mechanism helps ensure that query latency remains predictable. So on the execution side, Doris also apply a series of runtime optimizations. For instance, the dynamic partition pruning generates the predicates on partition column at runtime, so allowing unnecessary partition to be skipped. So like in the top one query, like you select star from a table, order by some column and limit like 10. So Doris used a two-stage access strategy to avoid reading unnecessary columns. So all these technologies are designed to minimize the unnecessary I/O, improving overall query performance and keeping latency under control. Okay, the third part focuses on the open file format. So Doris provides a fully native Parquet reader that implements with the vectorizations. So on top of that, Doris implied a wide range of optimizations specific to file formats. For example, it pushed down predicates and leverage Parquet, a row group index, a Bloom filter index, and page index to prune unnecessary columns or pages. Additionally, features like lake materializations help reduce the I/O under the high selectivity conditions. So all these optimizations together significantly improve the query efficiency when working with open file formats. Okay, so in summary, this series of optimizations across the I/O, the scheduling, and the file formats. So Doris has significantly reduced the latency of accessing lake data, so providing a solid foundation for real-time analytics. Okay, so next, I'd like to introduce the most important feature, the materialized view, which we call the bridge between the lake and the database. So materialized view provide a way to combine the data, computation, and the persistence, which help reduce the runtime computation. This is especially beneficial for the complex analytical queries where they can deliver significant performance improvement. So as you can see in the diagram on the right, a materialized view acts like a bridge connecting the data in the lake with the database query engine. So compared to other query engines, so Doris' main advantage is that it has its own high efficient internal storage format. So materialized view built on top of this format can provide much better access performance than formats like Parquet or ORC, so further enhancing the query efficiency. So for query accelerations, Doris query optimizers supports a transparent rewrite. This means users don't need to modify their original SQL or even be aware of the materialized view. So the optimizers, the optimizers automatically detects the matching materialized view and use them. So it can even combine partial data from a materialized view with the original data to return result, enabling data administrators to transparently accelerate query for users. So regarding the data freshness, so Doris supports the materialized view fresh scheduling ranging from seconds to minutes. So additionally, it supports the partition level incremental refresh, which help minimize the overhead of refreshing materialized view data. Okay, so in real-world user scenarios, so we can see that a carefully designed materials view can deliver huge performance improvements. So this is expected. If a query hits a material view, there's a virtually no runtime computation requirement at all. So this makes the materials view particularly well suited for online real-time business workload. So at the same time, from the perspective of data correctness and freshness, so Doris provide flexible strategy to control the materials view usage. For example, you can set a tolerable data latency, so allow users to balance the data freshness and query performance according to their needs. So all right, that concludes our introduction to the Doris technology for the real-time queries on lake tables. So we've not only covered the Doris core capabilities as a database, like real-time data ingestion, update, and query performance, but also the optimizations that we have implemented, especially for the lake tables, like including the I/O, the task scheduling, the file reading, and the material view. So now I'd like to briefly share the Doris current and the future plans for contributing to and integrating with the data lake ecosystems. Okay, so now this is an overview of about what we've done and will do in Apache Doris to support Iceberg and Pymon. So these formats are what Doris currently mainly focus on. So for Iceberg, we've got solid support already. Things like the catalog integration with Glue, the Iceberg REST catalog, the basic query on the V1 and V2 table formats, like the append-only insert, the time travel, the schema challenge, and the branch and tag management. And plus, we are working on supporting the V3 table format and the variant data type, and also delete and update support. And for Apache Pymon, this is another famous open table format. So currently support features including like catalog integration, the basic query with deletion vector support, and time travel, the batch incremental read, and also the branch and tag reads. So on the roadmap, we are adding the write support and the DDL support for the Apache Pymon table. So Doris is making sure that you can leverage both Iceberg and Pymon fully. So whether you are using what's available now or looking forward to the upcoming features. Okay, so with these capabilities, so the user can perform the real-time analytics on data lake tables, including the mixed workload. At the same time, they can also leverage Doris' write capabilities to perform lightweight data processing on the data lake tables. Okay, so now I would like to introduce two user stories to show exactly how Doris can improve the data lake analytics. So the first one is a quick story about how a leading cloud vendor built a modern unified lakehouse with Apache Doris and Apache Iceberg. So before the change, their data platform was really fragmented. So they were running multiple systems for data lake and warehouses. That means slow queries, duplicate data, and a lot of efforts just to keep things running. So they decided to simplify everything. So by combining Doris for real-time high-performance analytics and Iceberg for the open, reliable data storage, they create a single unified architectures. So Doris can query Iceberg table directly, so use materialized view and even catch hot data. So all of which make analytics much faster and more efficient. The results were very impressive. They now run over 20 projects across the 50 clusters and more than 2,000 nodes. So managing more about 15 petabytes of data. The query performance improved dramatically. So in some scenarios, they hit about 8,000 to 15,000 QPS, and the storage cost dropped by around 80% compared to their old ELK systems. So in short, these projects show how Doris and Iceberg together can truly power large-scale real-time analytics with better performance, low cost, and much simpler data stacks. Okay, so another one is Xiaomi. So one of the world's leading technology company. So they needed a data architecture that could keep up with this global scale, the powering analytics for like a smartphone, the IoT, and the electric vehicles. So their previous system were also fragmented. So multi-engine like Presto, Dreid, and Spark, and also Doris with duplicate data across the Iceberg and Pymon. And this complexity led to high maintenance cost and inconsistency query performance. So to solve this, they built a unified lakehouse using Doris and Pymon. So Doris provide a real-time high-performance analytics with its own storage and materials view. So while Pymon offer a low-cost, flexible data lake storage. So together, they deliver a seamless integration. So fast query, simplify governance, and low infrastructure cost. The result is they achieve up to a 6 times faster query performance, unified data access across all workload, and a simpler, more scalable platform. So empowering the team with a real-time insight at global scale. Okay, so that's all what we want to share in this session. So before we wrap up, I'd like to briefly introduce Apache Doris community resource. So Doris is a very active Apache project with vibrant communities. So we now have more than 700 contributors and over 14,000 stars on GitHub and more than 5,000 enterprise users. And we warmly welcome everyone to explore and get involved. And there are plenty of use cases, learning resources, and contribution guides available. So you can also find multiple channels to contact with the community and get support to share ideas. Okay, so that's all of today's talk, and thank you for your time and attention.